In this video, we'll be looking at some basic operations using complex numbers. So complex numbers can be added, subtracted, multiplied, and divided, just like regular numbers. In general, the solutions obtained when performing these operations are presented in the standard form a plus bi. So if you've got any I squareds, I cubes, I to the 4, whatever, you want to simplify those that it's just in terms of I. So in terms of our complex numbers, instead of working on the Cartesian plane, we work on what we call Argand diagrams. So the horizontal axis is referred to as the real axis, and the vertical axis is referred to as the imaginary axis. So if we were to graph 3 plus 0i, a would take us from the center to that point, so 3 to the right will give us a equal to 3 plus 0i. b, 0 plus 2i is going to take us 2 units up. c is negative 4 plus 5i is going to take us up to here. So c equals negative 4 plus 5i. d is negative 3 minus 4i, so we go negative 3 minus 4, or 3 to the left and 4 down. That gives us d. And then lastly, 2 minus 2i is going to take us over here, and that brings us to e, which is 2 minus 2i. So some things to note. Very similar to vectors, but instead of having an I and j component, they've got a real and imaginary component. Very similar to just graphing on a Cartesian plane, because negative is to the left and negative is down. So note that our imaginary axis is not labeled I, 2i, 3i. It is the imaginary of z. So the way we label our two components is our vertical is m of z, and our horizontal is real of z. So we have no I in our y-axis. All right, so addition of complex numbers. Addition is performed by adding the real and imaginary parts separately, very similar to adding I and j components of vectors. So z plus w is going to be a plus c plus bracket b plus d I. Subtraction of complex numbers, very similar. We're going to get a take c plus b take d I. And we can see over to the side here some wonderful images of a vector space of this addition and subtraction. So we can either add z2 to z1, as we see in this green line here, or we could add z1 to z2. So that's our commutative property. All right, last one, multiplication by a constant. If k is real and z is a plus bi, we're of course going to get ka plus kbi. And those are our three main operations that we're going to do. So geometrically, this is called a linear transformation, or the other way we can refer to that is dilation. So let's put this into practice. If z equals 1 plus I, and w equals 2 minus 3i, and v equals 6 plus 10i, evaluate z plus w and represent on an Argand diagram, and then 4z minus 3w plus 2v. Let's see, do we have more space underneath? Nope, this is what we've got. So z is 1 plus I. We want to represent this on an Argand diagram. So z is 1 plus I. W is 2 minus 3i, so that's going to come through like that. If we then were to transpose this, we expect our answer to be coming through like this. So let's see this interplay. We expect a large real component and a slightly smaller than 3 imaginary component. So we get 1 plus I plus 2 minus 3i. That's going to give us 3 minus 2i, just as we suspected. And in part B, we'd have 4 times 1 plus I minus 3 times 2 take 3i plus 2 times 6 plus 10i. So doing this component by component, we're going to get 4 minus 6 plus 12 as our real, and we're going to get 4 minus 9, sorry, plus 9 because it's negative 3 and negative 3, plus 20, and then all of that is our imaginary component. So this is going to give us 6 plus 13, 33i. And that's that for example 6. So if we want to multiply two complex numbers by each other, we use FOIL. That is to say, a plus bi, c plus di. We're going to get a times c, a times di, b times ci, plus bdi squared. That, of course, then becomes minus bd. So our real component is going to be ac minus bd, and our imaginary component is going to be ad plus bc. So let's see that here. So we've got 6 take 2i multiplied by 3 plus 4i. That's going to give us 18. It's also going to give us 24i. It's going to give us minus 6i, and then it's going to give us minus 8i squared, which is plus 8. So that is equal to 18 plus 8 as our real, plus 24 minus 6 is our imaginary, and so we'll get 26 plus 18i. And that is expressed in Cartesian form. Example 8, we're asked to simplify 2 minus 3i times 2 plus 3i. I want you to take a moment to recognize what is that the general form of. That's correct. It's the difference of perfect squares. So what we're going to end up with is a squared plus b squared, where a is 2 and b is 3i. But let's see how we go with this. So distributing this out, we get 4, we get plus 6i, we get minus 6i, and that's where the cancellation happens. And then we get minus 3i times positive 3i, so that's going to be minus 9i squared. And so doing this, we get 4 plus 9, which is equal to 13. So it's not the difference of perfect squares, it's the addition of perfect squares, because of that property that when I gets squared, it becomes negative 1. So interesting property of a new form of a plus bi, a minus bi. Okay, example 9. I think this is the last one. Nope, it's not. Determine the real of z squared w plus the imaginary of zw squared for z plus 4i and w equals to 3 minus I. So first of all, let's consider z squared w. That's going to equal 4 plus I times 3 minus I. So that's going to give us 16 plus 8i minus 1. So I'm skipping a couple steps here because we're getting more comfortable, times 3 minus I. So turning this into a plus bi is going to give us 15 plus 8i times 3 minus I. So in this case, we're going to get 45. We're going to get minus 15i plus 24i minus 8i squared, which is plus 8. So this is going to give us 53 plus 9i. I believe. Yes, 9. So that is our zw squared. Then we need to find our, sorry, that's our z squared w. Now we need to find our zw squared. So that's going to be 4 plus I, 3 minus I, 3 minus I. And again, I'm going to do my square first because I can apply binomial expansion. So we're going to get 9 plus, no, sorry, minus 6i. And then we're going to get minus 1. So it's going to be 4 plus I times 8 minus 6i. And so now that's going to give us 32 minus 24i plus 8i plus 6. Again, that's negative 6i squared, skipping steps. 38 minus 16i. So that is that. So if we wanted to find real of z squared w plus imaginary of zw squared, that's going to equal, so real of z squared w is 53, imaginary of zw squared is negative 16. Notice we have no I, that means we can actually compute this, so 53 minus 16 is going to be 37, I believe. Yeah, 37 plus 16 would be 53, yep. So that is our answer to that. Now, if we want to multiply our function by I, so just I on its own, x is of course going to become xi, and then yi is going to become plus yi squared, which is xi minus y, but if we want to write it in the correct form, that's going to be negative y plus xi. So what we notice about this is that it's transformed the line to be 90 degrees to where it started. So we've just been doing matrix transformation, so it's kind of like a rotation of 90 degrees multiplying by I. So it's clear from the diagram that IZ is a rotation of 90 degrees anti-clockwise from Z, which is a linear transformation. All right, next step to look at, equality of two complex numbers. What does it mean for two complex numbers to be equal? So Z is equal to W if and only if A is equal to C and B is equal to D. Note, the condition if and only if means that both of the following situations must apply. If Z equals W, then A equals C and B equals W, and the converse, if A equals C and B equals W, then Z equals W. Sorry, B equals D. I don't know why I said W there. So let's find values of x and y that satisfy the following equation. So we get, if we were to expand this out, 3x is our first term, plus 3yi, plus 4xi, and then minus 4y, because again we've got that I squared, which becomes negative 1. So our real component is 3x take 4y, and our imaginary component is 4x plus 3y. So we want to satisfy 3x take 4y is equal to our real component, which is 29, and we also want to satisfy 4x plus 3y is equal to, so I'm going to multiply equation 1 by 3. That's going to give me 9x minus 12y is equal to 87. And I'm going to multiply equation 2 by 4. That's going to give me 16x plus 12y is equal to 88. If I then add those two together, I get 25x is equal to 175, which means x is equal to 7. So if x equals 7, we get 3 times 7 minus 4y is equal to 29. So minus 4y is equal to 29 minus 21 is just 8. So y is equal to negative 2. So we get x equals 7 and y equals negative 2. And that's all for this video. Thank you very much for watching.